Chapter 9 Model of the System. Exercise 9.1. Using the model-oriented approaches with the example graphic program described in section 9.2.3, specify the move operation as the schema which acts on the currently selected object. Is the operation you have defined cumulative to successive move can be done as one move which is the sum of the other two, or is it forgetful? Discuss the implication of the framing problem in your definition. Answer: students might not have a great familiarity with the Z notation used in these textbooks, especially if they do not have a computer science background which emphasizes formal specification. Nevertheless, we will provide a model answer to this exercise in the Z notation and leave it to the instructor to decide whether an alternative language can be used to express the same idea. To accommodate the specification of the move operation, we will first need a function which allows us to add two coordinate points together. We just provide the declaration of this function here. Point. The motivation for this function is so that we can define a move operation with a single argument called delta below, which will specify how far to move the centers of every select shape. These approaches using relative movement will allow for two consecutive moves to be defined, with the overall movement being the sum of the individual moves. Another approaches, which will be quite cumbersome to define for a set of select objects, will be specify the move operation as an absolute operation. The argument to the move explicitly indication the new value for the center of each select shape. This operation definition will not be cumulative. Model. Initially, we might want to define to move operation simple to update the center position of a selected shape. Move state delta point id selected shape id center equals shape id center plus delta. There are a number of details in this defined operation which are left dangerously open to interpretation. Many of these are farming conditions of move operation. For example, what happens to shapes which are not selected? The normal intuition on this operation would be that they stay put, but the above definition actually allows them to change in any way, including the possibility of disappearing altogether. To ensure that unselected objects stay the same as they were before the operation, we will have to add a predicate to the definition. Move state delta point id select shape id center equals shape id center plus delta id DOM shape selected shape id equals shape id. We also need explicit state that no new shapes are introduced into the system, that the domain of shape remains the same. Move state delta point id select shape id center equals shape id center plus delta id DOM shape select id shape id DOM shape equals DOM shape. For those familiar with Z, it is possible to collapse the last three predicate in the above schema to the to one predicate using functional overriding from the basic Z mathematically toolkit. See SPIFFE GM, the Z notation, a reference manual, Prentice Hall. Another framing issue which has impact on the interactive style of this graphic system is specifying what happened to the select set of shape after the move operation. Our current definitions say nothing about this. Two clear options are whether the set of select shape remain the same or become the empty set, no select object, for reason of compositionality for defined consecutive move operation or consecutive operation targeted at the same set of shape. We choose the former option and specify this below. Move state delta point id select shape id center equals shape id center plus delta id DOM shape select id equals shape id DOM shape equals DOM shape select equals select. Note: experienced Z user will probably choose the functional overriding operator to more concisely express the first three predicates above. Exercise 9.2. Write a similar schema for resize. It should have the following informal schematic. The width and the height attribute are the shape bounding box. The resize operation should make one corner of the bounding box be at the current mouse position, simply as the argument current pose. Hence, the width of the box is twice the difference between the x-coordinate of the center and the x-coordinate of any corner. Width equals 2j center x corner x. Answer: strictly speaking, there are some errors in the Z usage for the hints in this exercise. The type point is not schema type, and so it is not meaningful to same schema selection as in expression like center x and corner x. The alert Z students should pick up on this error. However, sprint of the hint is still valid. To make things legal in Z, we can change the declaration of point as follows: point x, y, r. To be specified this resize operation, we will require to explicit model the bounding box of a shape. We introduce a type called a bounding box which will represent the corner of the surrounding box, which define the extent of the shape. In figure 9.1 we have drawn the bounding box for the cycle, but we have not made the information explicit in the specification in the text of this chapter. We omit detail in this sample answer on rectangular constraint. We omit detail in this shape answer on rectangular constraint for the corner of the bounding box. Sample: the upper left and right corner have the same y coordinate value, but the x coordinate of the upper left corner is strictly less than the x coordinate of the upper right corner. Bounding box: upper left, upper right, lower left, lower right. Point: upper left x, upper right x, upper left y equals upper left y. We can add the bounding box as information to know about shape, but extend in the definition of shape a constraint on the bounding box motivated by the hint to this exercise is that its width and height are the same as the width and height of the shape. In addition, the central coordinates are related to the width and height. Note below that we use the name height and width in the definition of shape to increase its readability. Shape type, width r, height r, center point bb bounding box, width equals 2, center x bb upper left x, height equals 2, center y bb upper left y, width equals bb upper left x, upper right x, height equals bb upper left y, bb lower left y. Resizing can be viewed as changing the size of the bounding box. At the relatively abstract level, we can simply specify the resizing operation with a single argument indicating the new bounding box for the selected shape. A precondition for the operation is that there is only one selected shape. Resize state new bb bounding box select equals 1 id select shape id bb and new bb. For elite dome shape select id equals shape id, dome shape equals dome shape, select equals select. Exercise 9.3 in section 9.2.5 we set the specification algebraic z-draw could be extended to say that a move resize or unselect after a delete has no effect. The axiom for unselect look like this: ix unselected delete g equals delete g. Write two more axioms x and xi which say the same above move and resize. Now show the axiom iv and v to show that ix implies both your new axioms. Answer: the three additional axioms are 9. Unselect delete st equals delete st. 10. Move p select st equals delete st. 11. Resize p delete st equals delete st. Axiom 4 and 5 are 4. Move p unselect st equals unselect g. 5. Resize p unselect st equals unselect g. To show that axiom 10 is derivable from axiom 4 and 9, we can argue as follows: move p delete st equals move p unselect delete st by axiom 9 equals unselect delete st by axiom 4 equals delete st by axiom 9. A similar argument shows the axiom 11 as derivable from axiom 5 and 9. Exercise 9.4. A two-function calculator has the following button: 0 until 9, plus, minus, and equals. The would compares the command set C of the pi model of the calculator. The state E would consist of the three components: the two current numbers being entered, the last number to be operated on, and the pending operation plus or minus. The display D is simple is side number. For this example, ignore the result. Write down semi-formally the do function updating the state for each user command and the display function relative the state A to the current display D. To check your definition, what does the display have on it after the user has entered 2 plus 3 plus most calculator will show 5. Does yours? Consider the display after the sequence 2 plus 2, 2 plus an effect on each of additional user input of 3. Does the calculator satisfy the transparency property? Answer. The definition of the do-it function could process as follows. We will use the Z notation is still simple as what. The character set is defined as C0, 1, Z2, Z3, Z3, 4, 5, 6, 7, 8, 9, 0 plus equals. It will be useful to distinguish the digits and operation plus and digit PC or PC digits F 0 1 2 3 4 5 6 7 8 9 0 G OP equals F plus G. The state is defined as an order for tuple consisting of the current number being entered, the last number to be operated on, and the pending operation. E equals set digit OP. The display is simply a project of the current number being entered. D equals set digit. Display D a current last OP. A display current last OP equals current. The do-it function is defined below by case exhaustion. The notation of C1 meant to apply operation O0 to the argument C and I, so that 2 plus 3 would be written plus 2, 3, which O equals plus C plus 2 and L plus 3. Do it AC1 set digit D digit OP. Do it CLO OCL 0O. Do it CLOD equals DCO if last key 2 F plus equals G. Then C plus D LO. Otherwise, do it CLO equals OCLCO. The following table traces the execution of the calculator. CED 00 plus 0, 2, 2, 0 plus 2, plus 2, 2 plus 2, 3, 3, 2 plus 3, plus 5, 3 plus 5. Compare the trends table for the programs 2 plus 3 and 3 plus 23. CED 00 plus 0, 2, 2, 2, 0 plus 2, plus 2, 2 plus 2, 3, 3, 2 plus 3. CED 00 plus 0, 2, 0, 2, 2, 0 plus 2, plus 0, 0 plus 2, 2, 2, 2 plus 2, 3, 23, 2 plus 23. Notice the display after the program 2 plus is the same as if after the program 2 plus 2, yet the behavior of the subsequent 3 command is different. Therefore, the calculator as defined does not satisfy the transparency property. Exercise 9.5. Imagine a calculator normal accept the display A for 0, B for 1 up to G for 9, so the number 372 will appear as DHC. Does this affect the formal transparency of the calculator? Should it? Answer: formally, this would not affect the transparency property of the calculator. Any function from this display to effect which help from the number would also hold for their alphabetic counterpart by just composing it with B code A for 0, B for 1, up to G for 9. Of course, most people would probably find using the ENCODE calculator quite a bit more difficult than one which used the normal 10 digit. The important lesson here is the formal expression of the transparency property does not indicate how difficult it is for humans to determine the function between display and effect. The formal expression just requires that there be some function. In practice, human users would probably judge the ENCODE calculator as unpredictable, that is, not transparent. The moral is that even though we can capture a usability property formally does not mean that we can capture the entire intent of the property. The transparency property will have to be argument in order to measure the complexity from the user perspective of the function between display and effect. Exercise 9.6. Can you suggest any improvement to the screen button feedback problem discussed in section 9.4 that would distinguish at the interface between the two cases of hitting or missing the button? Is there any guarantee with your solution that the user will notice the distinction? Answer: some suggest fix to the button feedback problem would be to have the function attached to the button be invoked when the mouse key is pressed down rather than up, but the solution would not work for function invoked one pop-up menu. Another possibility is have some possible and audible feedback from the button as associated with the invocation and for of the function on the mouse key release. This solution does not guarantee that the user notices the added effect unless their attention is focused on the added visual or aural effect. Another possibility, subtly different from the last suggestion, would be to associate additional verbal or aural cue to the error case when the mouse accidentally slip off the button between the press and release of the mouse key. Chapter 10. Implementation support. Exercise 10.1. In contrasting the red evaluation loop and the notification-based paradigm from interactive program construction of the preemptive dialogue was discussed. How a program describe a preemptive dialogue by purely graphical means? Answer: creating a preemptive dialogue by graphical means is quite simple in a graphic-based interaction. It is assumed that the user can only interact with the part of the system that are visible. In a Windows system, for example, the user can only direct input to a single current selected Windows, and the only means of changing the select window would be by indicating with some gesture within that windows. To create a preemptive dialog, the system can produce a window which covers the entire screen and make it the currently selected window. A user input will then be directed to the windows and the user will have mean of selected another windows. The covering windows choose preempt any other user action except that which it is defined to support. Exercise 10.2. Recall the state transition diagram for font characteristics present in the Chapter 8, Section 8.3.3. Compare different interaction objects with a could implement this kind of dialog. Use example for existing toolkits pull-down menu or dialog box, or create a novel interaction object.